Maybe we could.
I'm not allergic.
It's okay.
Anyway. Yeah.
Okay, go ahead.
Okay. Yeah. So, hold on. This out. Okay. So welcome everyone. So today we have Wenjun Dong. He is a research scientist at Center for Space and Atmospheric Research at Embry-Riddle Aeronautic University with a primary workplace in Boulder, Colorado. He also served as an adjunct scientist in Gates. So his research centered on gravity wave modeling, including their generation, propagation, breaking, and interaction with background atmospheric condition. He works extensively in both high-resolution regional and global circulation models and collaborates closely with modeling team in Embry-Riddle and Gates. Dr. Dong is also advancing the use of artificial intelligence in atmospheric science, developing machine learning models for simulating gravity wave and global dynamics, and exploring AI-driven approach to gravity wave parameterization in global model. So today he's going to talk about the secondary gravity wave.
Yeah. Okay. Thanks for your invitation. Yeah, I'm glad to share our recent works. So today I'm going to talk about something about second gravities in the MLT. Yeah, apologize for the long vacation. So yeah, I want to thank my collaborators, Dave Fries, Tom Sland, Alan Liu, Jiahui, Jin Tai, and other people. So gravity is kind of disturbances in the atmosphere. So they are always generated in the lower atmosphere, then propagate upward. The common source include the volcanic eruptions, convections, and thunderstorms and others. So once they generated, so they will propagate upward. Because the density is decreased with the altitude, so the amplitude of the gravities will increase with the altitude. Once they propagate in the upper atmosphere, so they will deposit the momentum and energy into the mean flow and alter the mean flow. The mean flow alter will also in turn alter the phase speed of the gravities. So I will use the example to show how gravities propagate upward. So here is the example of the gravities breaking and secondary gravities generations. So in this case, we introduced the 3D Gaussian package in the lower atmosphere. Then you see at the beginning, for example, at the 10 minutes. So here is the
point?
Yeah.
No, we don't have pointer. Is that? I don't know. Is this the right one?
Okay, that's okay. Yeah. So for example, at the 10 minutes here, you can see the gravities. The gravities are almost linear. Yeah, almost linear. So, but when they propagate upward, they will deposit the momentum into mean flow. The mean flow will be accelerated. So the accelerated mean flow will in turn accelerate the phase speed of the gravities. So that's called the self-accelerations. You see, but the moment flux is uniform in the gravity package. So in the package, you say in some place the moment flux is large, with another place. So you see here, actually, the moment flux in the center of the package is larger than other wells. So the acceleration will be larger than other wells. So for example, the gravity package like this, once they accelerate, they will like this, occur a strong kinking here. So here is a strong kinking here. Yeah. But as they propagate upward, the acceleration will become stronger. So the phase kinking will become stronger. But the atmosphere accounts for such large phase kinking, so they will become breaking. So when they breaking, they will generate strong second gravities here. Yeah, you can see a lot of second gravities here. And here at the later times, you can see a lot of strong second gravities. During this case, we can see many scale structures, for example, small scale structures like instabilities here, and the small scales strong phase kinking here, and large scale structures here and here. So it's challenging to capture all these dynamics in local simulations because we want to because those dynamics cause significantly different scales. Yeah, from small scale instability to large scale tidal motions. So the periods will from minutes to days. The spatial scales will from meter to kilometers. So it's hard to capture all these dynamics in a simulation. Here we want to introduce the CGCAM. It's a local hydrogen model. It's based on the FV3 framework. We have developed new capabilities for this model. We include two features we want to introduce. The first feature is the stretch on the block grass. So, for example, see this figure. So in this case, we can use the very high resolution phase in the instability dynamics. But for other cases, so for example, here and here, because they are very strong second gravities, they are large scale, so we can use coarse resolution. So that's called the stretch on the block phase. So and also we also include the data estimation techniques in the model. So in this case, we can incorporate the large scale waves in the simulations. We can, for example, we can include the webcam simulation data set. For example, if we run the webcam, we can run the 0.25 degrees resolution. After we get those data sets, we can add the input of the CGCAM to drive the CGCAM. So in this case, if this case, we can use we can see how the global scales to influence the small scale structures. Yeah, and that's a bit. I will show you some simulation results. So in this case, we want to we use the CGCAM to do a simulation about gravity breaking in a tidal wind. So in this case, we are focused on this mountain. Here the figure we saw when the wind flowing over the mountain, there are many gravities generated, and they will propagate upward. In the Mesosphere, there was a tidal wind. The tidal wind will influence the instability structures and second gravity generations. And in this case, we improve the tidal wind using the data simulation techniques. And so the tidal tide has some technical characteristics. Yes, for example, the vertical variance is 30 kilometers. The amplitude is 65 meters per second. So the tidal wind can. Here is the movie of the tidal wind. Influence the gravities. This panel shows the total wind. This includes the gravities and tidal wind. This panel shows only the gravities. This panel shows the gravities at XY plane, so at different altitudes. So you can see the tidal wind can influence the gravities. You see they block the gravities propagating upward here. So this is because the tidal wind can create a critical layer for the gravities. The critical layer means the mean wind is equal to the background wind. So because there are mountain waves, so the mountain waves phase speed is 0. So the critical layer is just here because the wind is 0 here. Yeah, you can see if the gravity wave propagating upward, they will encounter the critical layers. When they encounter critical layers, the vertical wavelength will decrease. When the vertical wavelength decrease, the group velocity will also decrease. So they will. So this means the energy will concentrate in the near the critical layers. So you can say many energies concentrate near the critical layers. So let's say how the tidal wind can modulate the gravity waves. We calculate the energy flux and motion flux and the heat flux. So you can say here is the energy flux, here is the motion flux, and here is the heat flux here. So we can say the gravity waves can the tidal wind can influence the gravity wave period with a 24 hours period or decay. Yeah, you can see here is the 2 hours, 24 hours. Yeah, the gravity waves can also influence the tidal wind structures. So here we calculate the mean wind and the mean temperature. You see, if the gravity wave energy concentrate near the critical layers, so they will deposit the energy near the critical layers. You will see, yeah, you see that here is the wind change, here is the temperature change. You can say near the zero wind, here the wind, there are large wind change here and here. So yeah, so it means that the gravity is also impact the headwind. We also compare our results with the observations. You see here the kind of observations. We see both kind of city observations will show the gravity waves oscillates in phase with the tide with its peaks occurring near the regions of zero wind. It's quite layers near the zero winds here and here. This is observations, and this is the simulations. We can see the similar results. Here is another comparison between the observations and simulations. So here in the TZ plane, so you can see it lacks the virtual radar here. You can see the tidal wind can modulate the instabilities and small scale structures here and here at the 24 hours period. And you can the tide can also influence the second gravity generations. You see, here are lots of small scale structures, high frequency gravities, and large scale, low frequency gravities. Those gravities have periods course from the several minutes to the 4 hours. Yeah, you see, yeah. And we see the similar results from the kind of observations. So you see here above the 90 kilometers, the small scale structures create bowl-shaped structures. Yeah, you see like these structures. They also have 12 hours period. Yeah, similar structure here. Yeah.
Oh, sorry. What are the curves? The black curves here in both plots?
Yeah, I just want to show the both structures here.
The structure of the
bowl. This bowl. Yeah.
In the gravity wave activity.
Yeah.
Oh, I see.
Yeah, second gravities here above the 100 kilometers.
Okay, I see. So yeah, there's a clear increase of activity in that in that region or above that altitude.
Yeah.
And are you saying those are from the secondary waves?
Yeah.
I see.
Yeah, we see the similar structures from the observations here. Yeah, in those cases we show the we show the how gravities breaking can create second gravities and how the background can influence the second gravity structures.
Oh,
Next,
I have a question. These two comparisons seems to be at completely different altitude. They are 20 kilometers away.
yeah, because yeah, here we just want to show these structures like these structures
Oh,
here and here. Yeah, but they are in the different altitudes, right? Yeah, because they are not in the same case. This is the idealized conditions. That's from using idealized tidal wind, but this is from the observations. So they may the tidal wind may in a different altitudes.
Basically, observation, do you see this every day or is it just January 17th and 18th? Is it like very common?
Yeah, it's really very common in the observations. We just select one case from the observations.
And for the model, do you know why it follows this nice curve like the?
Yeah, I'm trying to, yeah, understand this, but but maybe I need to explore it further.
Okay.
Yeah, but I think it's because the tidal wind blocks the gravities. Yeah, and the gravities concentrate the energy near the critical layer and fuse the energy to the upward.
Yeah, I was just wondering if you have a symmetric wave source, the wave response may alternate, but I don't see how the tidal wave would create, up and downs. Is the wave source you specify, is that kind of symmetric?
Yeah, you see, if you see the movie, you can see many it's yeah. You can see the sun gravities become stronger and become weaker during some yeah. You see here. You see this bigger moving. It becomes stronger and become weaker. Become stronger, become weaker in the tidal wind.
Interesting.
Yeah, next we will use we want to use the webcam CVC data set to drive the CGCam to see how the realistic tidal wind impact the gravities. Okay, so we show some examples of how the gravity breaking introduced generated the second gravities. So next we want to talk about another second gravity source. It's called instabilities. So here we'll show some examples. So here are the solutions from Dave. So in this case, we run several the solutions. So here are 5 panels. In the first panel, we use 500 meters, and in the second panel, we use the 1 kilometers, and in the third panel, we use 2 kilometers, then 4 kilometers, and 8 kilometers. So we see when we use very high resolution, solutions. So we see strong instabilities here. Yeah, we see strong instabilities, and we also see the strong second gravities. But if we use very low resolution, for example, we use 8 kilometers, we can't see any instabilities, and we can't see stronger second gravities. So this means the instabilities may play an important role in the second gravities. Yeah, here is another case. So we see, in this case, we see before gravity peaking, we see some weak second gravities. So this must from the body forcing, but before the gravity breaking. So after gravity breaking, they will create stronger instabilities and then stronger second gravities. This is another case we want to show instabilities may play an important role in the second gravities. So we will show you another recent works. So in this work, we know KHI is an important stability in the atmosphere. So they are from the data observations. We did a statistic analysis with over 1884 observed days. We see 18 KHI, 80 KHI days. So this means the KHI accuracy rate may be larger than the 20%, because we only pick up the very clear KHIs. So we want to show we want to show KHI is very common features in the atmosphere, and we also want to show some queries generated by the KHIs. Next, we will show our simulations observation results from for the KHI generated graduates. Here are the data observations from the Alaska observations. Here we show data observations. Here is the data observations solid data. We see clear KHI structures here, and here. And the second here is the density perturbations. We also see some small scale structures. They are the KHIs. We also use another observations, but they are in the same station. So it's really lidar. So we see lots of graduates from the KHIs. So we also calculate the KHI energy on the graduate peak. We see here the KHI peak, and there are 3 KHI peak, KHI peak 1, 2, and 3. We also find there are 3 graduate peak. For example, graduate peak 1, 2, and 3. Every peak just follow the KHI peak. So it means that KHI graduate energy is from the KHI. So we want to reproduce these results with our observations. So here is our background conditions. The A and B is A and B is the observed U and T lunar wind and temperature. For the background U and T, we just smooth the observed U and T, get the background U and T. So here is the lunar wind and temperature we will use for the simulations. We also calculate the result number from its U and T, get the result number. We say in some place the result number is less than the 0.25. It means there may be KHI. So here is our simulation results. We also see the 3 KHIs from the simulation results. For example, it's KHI 1, very clear KHI structures, KHI 2, and very clear KHI structures, and KHI 3, we still see very clear KHI structures. And here is the KHI region, KHI 1, and 2, and 3. From the 60 to 85 kilometers, they are showing the downward propagating gravity rays. So in this case, in simulation case, we also calculate the KHI energy and the gravity energy. We see 3 KHI peak. We see KHI peak 1, 2, and 3. And we also see the gravity peaks, gravity peak 1, 2, 3. And each gravity peak follow the KHI peak. It means the gravities were from the KHI. So this is another case that we show that KHIs stabilities can generate the graduates. You say that here is the full picture of the KHIs and the graduates. The KHIs can generate the both upward propagating graduates and downward propagating graduates. We zoom in the KHI structures, we see some interesting features. For the observation KHI features, we see some phase shape here. Yeah, you see strong phase shift and phase shift here and here. They have a period of 3 to 5 minutes. And we also see the similar structure from the CDCAM simulations. So we also see some phase shifts and the strong phase shift. The period is around 3 to 5 minutes. Actually, other observations also report the similar observation results. You see here, we show the phase shift and strong phase shift from other observations. So here is a KHI picture. Here is a spectra of from the KHI features on the gravity features. From the features we show, there are 3 regions. This region shows the KHI region. This region shows the gravity region, and it's 2 gravity region. We see that in the KHI region, the spectral peaks is around 6 to 7 kilometers. They have a small scale structure. Here is the KHI spectral peak. And you see for the graduates, you see the spectral peak is around 10 to 20 kilometers. The spectral peak just move from the KHI peak to the gravity peak. It means it confirms that again that graduates from the KHI. So here is a picture of showing how the gravities from the KHIs. They show some energy flow from for example, the KHIs come from the tidal wind, and then the KHI can transfer energy to the turbulence, then transfer energy to the mean wind. They can also transfer energy directly to the mean wind, and they can also transfer energy to the graduates. So here is the full picture of our future investigation. So for the primary graduates, they will transfer the energy to the large scale centigraves. They can also transfer the energy to the small scale centigraves, but they can also transfer the energy to the main wind. But for example, if we see that the primary graduates can transfer the energy to the there are many pathways to transfer the energy from primary gravities to the large scale secondary gravities. For example, from phase kicking and from the gravity braking and from the body forcing. And to the high frequency gravities, there are also many other pathways. For example, from the vortex ring braking and from the instabilities and body forcing and other ways. So in the future, we want to quantify how many energy will go into the large scale centigraves, how many energy will go into the small scale graduates, and how many energy will go into the mean flow. Okay, in the future, we are going to improve the CGCAM continue to improve the CGCAM. We have 3 directions. One is for the adaptive mesh refinement, because the current structure and progress are fixed and make adaptability in space and time. But instabilities can often evolve across both dimensions, both in the time and in the spatial. So in the future, we are going to developing adaptive mesh refinement to check and resolve the moving instabilities. And secondly, we are going to develop a new GPU-based version of the CGCAM. And in the future, we also want to focus develop a 2-way coupling with the global models, because data estimations in our CGCAM can quantify the impact of the global scale dynamics on the local systems, but does not capture the feedback from the local dynamics to the global systems. So in the future, we want to build a 2-way coupling between the CGCAM and the global models, for example, like MX. So next, we want to talk more about our machine learning efforts for the gravity simulations. So solving the Navier-Stokes equations for the gravity distributions at small scales is challenging. So in the future, we are going to use the machine learning to approximate the Navier-Stokes equations. There are some difference between the numerical method and the machine learning. For example, for the numerical method, they are slow on the fine grades but fast on the coarse grades. For the machine learning, they are slow to train but fast for the inference. In our machine learning model, we use the transformer architecture. So there are many similar structures between the transformer and the numerical method. For example, the core of the transformer structure is a self-attention. The self-attention means we can capture the interactions between the tokens or patches. But for the numerical method, we can say for the numerical method, our goal is to capture the interactions between the different particles. So that there are many similar things. We want to introduce the ChemNet. ChemNet is our machine learning model. So we have for this model we have two components. One is a backbone model, another is a tracing model, modular model. So this is inspired by the traditional models. For the traditional models, we first calculate the basic variables, for example, temperature, wind, density, pressure, and all these basic variables. So in this case, we also use a basic model to simulate the basic variables, for example, temperature, wind, and pressure, and density. And for the tracer variables, for example, O2 or other tracer variables, we use a fine-tune method. For example, we can fine-tune the basic model just by adding another 4 layers to fine-tune these 4 layers to prediction another tracer variables. Here actually we have two versions of the ChemNet. One is the local version, and another is the global version. For the local version of the ChemNet, we trained the ChemNet on the Kaiser student CityCam simulations. We saw some results we saw two cases. One is for the KCHI cases, KCHI generated gradually cases, and another case is the mountain wave cases. For the ChemNet, for the KCHI cases, we see the top panel is the ChemNet, the bottom panel is the CityCam. We see we can use the ChemNet can capture all the details of the KCHI structures, for example, small scale structures and some large scale structures. And for the mountain wave cases, we can also use the ChemNet to capture the mountain wave generations and the initial self-accelerations and gravity applications and secondary gravity generations. We can use the ChemNet to capture all these features. But you say, if we use the ChemNet, we can get results just less than 1 minute. For example, for the ChemNet, we can get the results with less than 1 minute. But for the CityCam, if we use the CityCam, we need to use 66 CPU cores to run half hour get results. So here is the global version of the ChemNet. So this global version is trained on the 10 years of Vectormax simulation data size. So we saw 2 altitudes examples. So they are showing the temperature at 90 kilometers and 250 kilometers. So you see all these features all these simulations can capture the large scale features very well. For example, here, ChemNet can capture the large scale structures, but miss the smaller scale structures from the vector max. So here are the tree survivals. So we train a candidate vector model to predict the O2 mixing ratio. We also get so here is the candidate, here is the vector max. We also see the candidate can capture well the large scale structures showing the vector max. Here's a full picture from we show the spectral structures. We see at the low altitude and the higher altitude, we see the spectral characters agrees very well. Here, and here. But at the mesosphere, you see at larger wave numbers, we see there are some difference between the candidate and candidate and vector max. This is because the candidate just treats the smaller scale structure as a noise, so they just remove all these small scale structures as noise. But in the future, we are going to improve the model to capture the small scale structures, and we are currently doing the same things to capture the small scale structures. So I'm going to show another model. So here is the graph distribution.
I have a question. So on the previous figure, you said the ChemNet may treat the small scale as noise. When you train, can you control it, like tell the package or the box to or define a scale that with the scale with scales size larger than certain size, then you treat as a signal, while only treat the smaller scales as noise. Can you define that when you are doing the training?
So in the future, we are going to add spectral laws in the training process. So if we add the spectral laws, so we can constrain that we for example, if we use the spectral laws in the training process, we can just constrain the spectral laws like this. So this will just improve the small scale structures here.
Okay. And another question is, why it's not a problem at lower altitude? It only becomes a problem at the mesosphere and higher.
But you see from this figure, this is the vector max. You see there are many small scale structures in the mesosphere, but you see from the lower atmosphere and the upper atmosphere, there are less small scale structure.
Okay.
There and there, and so they agree very well at the lower atmosphere and upper atmosphere. But we are training a new model to capture all these small scale structures. So here is another model. It's called graph diffusion model. So it's an encoder, processor, and decoder model. For the encoder, so we can map the latitude and longitude grids to the latent space. So if we map this into this latent space, we will have a uniform grids here. So they can have the uniform resolution everywhere. So firstly, map the grids to the latent space to get the uniform resolution. Then we just input all these variables into the processor. The processor is a graph transformer. It can calculate all the attention between different nodes. So it can capture all the interactions between different nodes to capture the spatial interactions of different variables. After this processor, we output the processor to the decoder. This decoder just map map the grids from the latent space to the longitude grids. So in this process, we add the diffusion process. At the core of the diffusion model is the addition and removal of the noise. So for example, during this processor, we just add noise, and during this process we just add noise. And here, after decoder, we just add the noise, just remove the noise. So this add noise and denoise just learn how to add the noise and remove noise to achieve higher solutions. So let's say or some solution results. So here is those. So this is trained on the higher solutions vector x. The size is 0.25 degree solutions. So here is we just map the higher resolution to lower resolution to degrade the resolution. So this is the low resolution field. It has a resolution of 2 degrees. So this is the resolution with 0.25 resolutions. So we use our graph diffusion model, convert the low resolution field to the high resolution field by adding the missing wave structures. So our model can be seen as a learned gravity wave parameterization. One that can progress. Today we construct the small scale structures that are missing in the group models. So you can say, if we have a low resolution model, we convert the low resolution to the high resolution model. So we see the spectral results. So the red line is lower resolution spectral characteristics, and the blue line is the higher resolution structures. So the black line is the difference between these two lines. So actually, the GDIT our model can improve the spectral characteristics. So in the future, we are going to combine the ChemNet and GDIT. It means that first we can use the ChemNet to get the coarse resolution, then use the GDIT to map the lower resolution to the higher resolution. So it can also be used for the gravity parameterization in the group models, because in the group models we are always missing the small scale structures. Through this way, we can just add all these small scale structures in the group models. So here is our future machine learning improvements. So the first is we use the ChemNet, improve the ChemNet, and just combine the ChemNet and GDIT for the improved solution handling. And we also, in the future, we also want to just include the GDIT in the ChemX, so it can be used for the gravity parameterizations. For example, we can just build a GDIT, build a framework between the GDIT and the ChemX for the gravity solution. So here are my summary. CGChem or model CGChem has reviewed multiple standard variable sources, including the vibrating body forcing and instabilities. And our machine learning efforts, including the ChemNet and GDIT, show the potential for developing a new gravity parameterization in the group models. Thank you for everything.
questions? As for this last part with the GDIT, do you have any sense of how much you still keep, say, like the seasonal and spatial distribution of the gravity wave, or do you just kind of preserve the spectra, but it's not preserve the distribution as it should be?
Yeah, because in GDIT we add the spectral loss during the training, so we can't train. But actually the blue line is the true spectra from the Vecmax. So this red line is a spectra from the ChemNet, or lower resolution. So if we use the GDIT, we just constrain that the spectral loss must follow the true spectrum.
Okay. Yeah. So I guess my question is, you could create this spectra to be this similar, but that doesn't necessarily mean it puts the waves in the right places.
Yeah. Actually, we also compare compare gravities. For example, this is the gravities we added to the higher resolution part. Yeah, you say this is the this is the lower resolution field. Yeah, we add those gravities into the lower resolution and get the higher resolution part. Yeah, we compare. We also during the training, we also compare this with the true gravities from the Vecmax.
Okay.
Yeah.
And they tend to agree in terms of seasonal variation. Then.
Yeah, but we only use 1 year of the space side because we only have 1 year higher resolution Vecmax.
I think we have a question from online people. Do you want to unmute yourself?
Sure. Hi, Wenjun. It's Chris Cruzy.
Oh, hi, Chris.
I have a few questions, but I'll start off with one that I put in there. So with the GDIT simulations, I was really looking at this figure C that you have up right now. I was just wondering, like, to what extent will phase relations, like the expected phase relations, be present in those higher resolution fields that you're trying to add on to a coarser resolution model? Like, will you be able to physically analyze those perturbations, or is that just going to be, like somebody else said, a spectral bump at higher frequency?
Yeah, for the graduates we added to the lower resolution, because for the loss we compare the true graduates from the Vecmax and the prediction graduates from the GDIT. Yeah, we have the error bars to show the difference between the graduates we added on the true from the Vecmax.
Thanks. And if there's time for one more, I'll ask another quick question. In your original simulations where you were forcing tides in CGCam, I've done similar stuff in the past, and when you get to those very high altitudes, especially if you have a mountain of like any amplitude, you have so much momentum deposition in regions where you have such low density that you get enormous mean flow changes. So I was wondering, how are you forcing the mean winds at and above, say, 100 kilometers in those simulations? And also, how are you forcing the tides, and to what extent can the gravity waves interact with the tides that you're forcing? Because I think the momentum deposition that you should be getting at those altitudes is probably enough to force mean flow changes on the same amplitude as your tides, if you weren't, forcing them to be some speed.
Yeah. In the first case, the tidal wind is introduced to the simulation. So actually, in this case, the tidal wind just as the background conditions, the wind is added through the momentum equations.
Yep.
Yeah, it's added to the momentum equations as the tidal wind forcing.
I gotcha.
Yeah.
you just have a certain tendency that you're adding that's horizontally homogeneous.
Yeah.
And above that, why do your winds not, why don't you see like negative 50 meter per second across the domain? Is that,
You mean this figure?
yeah. I guess why does your mean not drift above 100 kilometers?
Uh,
I can let that one go. But anyway, I appreciated your talk.
yeah, okay.
Any other?
Yeah, maybe my question is a bit related to what Nick was asking earlier. So now say if you are train your model, this is the last part. When you train your model and use GDIT to try to emulate the gravity wave effects, once you add that, your mean state, temperature, wind, everything can change quite a bit, because before that maybe the coarse resolution model is missing a lot of waves.
Yeah.
Now you're adding them in. So when those changes, will there be an interaction between the new waves you're adding and the mean flow? I guess I was trying to see if this the way you are doing this, will that capture the interactions between the wave, the small scale gravity wave you add, and the large scale state.
Yeah. For this case, we just I think in the future we can compare the simulations and the observations to check if the GDIT can capture the mean flow and small scale structures.
Right.
Okay, well. Yeah, but currently we during the training we only use using the error bar from using the spectral loss and the loss from we use two laws. The first loss is just compare the gravity waves, prediction gravity waves with vacuum X, and the other loss is the spectral loss. We just constrain is loss to the 0, 1. Yeah, we only use two laws, and we validated our results using the vacuum X simplicity size, but we haven't do the same thing on the observations.
So you mean that in principle it should be captured, but maybe the current training hasn't done that.
Yeah.
Okay.
Yeah.
Another thing is related to this is in the model, the spectral slope is actually a variable. It interact or feedback or respond to the wave force.
Yeah.
For example, it may become flatter when your wind is very large.
Yeah.
And it may become more steeper when wind is reduced by the wave. So it's not a constant value. So that kind of, again, that kind of feedback interaction will be important in this process.
Yeah. We also consider using just a spectral loss to train the model. Right. For example, we don't use any not use any desites, vacuum X desite. We just use the spectral loss because the spectra will have a negative 5.3 degrees. Yeah, we'll use this to train the model. In that case we will not use any desites. It's just physics informed.
Okay. You mean by the spectral from the model, not a fixed value from like a 5/3.
Yeah, that's using this spectrum. Yeah, that's using the blue line spectrum. So
Okay.
train the model.
I see. Yeah.
Yeah, like your papers. That's okay.
before the global. Yeah, the panels say, just by looking at this, there's like sort of horizontal line across all the latitudes.
Hmm.
I wonder if this is like structural lines or the panel C.
Yeah, fantasy.
Yeah, it just seems like more like horizontal lines. Yeah.
Like this
The streaks.
district.
Yeah. Yeah, this may be because
Just because Graceland?
yeah, this must be from the Recommended science.
This is the grading one.
Yeah, I think so. Yeah. You mean this is a small
Yes.
this structure there? Yeah, this may be because the bigger that's the probably scale.
The plotting issue.
Yeah, probably issue.
Yeah.
Yeah.
There was something happened with the,
Yeah, it's yes.
You can create 18 panels, say, for different season compare with.
Yeah.
And maybe because when you add the gravity waves, when you add the gravity waves, you add it grid by grid, right?
Yeah. Well, yeah, just 1 point by
1 point by point. Okay. I'm not sure if that's really also related to kind of pixelization. Huh?
yeah, I think it's because plotting issue.
Okay, yeah, I have another question for this part. So in this part, you have assumed using the low resolution temperature was on the wind and other kind of field, you created the high resolution output for temperature and lunar wind and other variables. So, but you have mentioned that you to apply the gravity wave parameterization. So did you compare the result for momentum flux or momentum budget or?
Yes, it's a good question. Yeah, we need to. It's because we can't. Yeah, we haven't compared the momentum flux and heat flux or these variables. Yeah, but I think it's a good reaction.
And may I ask that training data used for the high resolution Wacom X-ray data is the same as American
Yeah,
data?
that's right. It's the same.
If so, I think STSW is not included in this year. So I'm afraid that the gravity wave behavior during the STSW is not realistic.
Yeah. Actually, we need to. Yeah, we need to check this further to using more physics, for example, STSW and other physics. To test our model. Yeah, but we only have 1 year of precise.
Can I ask a quick question? For the earlier part of your presentation, you mentioned the CGChem model.
Yeah.
So does the CGChem model has some lateral boundary or?
Yeah, lateral boundary. Yeah.
So
yeah,
what is the boundary condition?
Yeah, we can use a periodic boundaries.
Periodic.
Yeah, but we have as the sponge layers.
A sponge layer.
Yeah, between different.
Not cyclic.
Yeah.
Just the sponge layer.
Yeah.
Any other questions or question from online people? If not, let's thank our speaker today again.
Okay, thank you.
It seems like you have a very long to do list.